All right, welcome to the third part of a series on machine learning with Spark and Cassandra. This one is focused on testing. Specifically, we'll be going over tests for binary classification models, regression models, and multi-class classification models. My name is Obi Anamnachi. I work with Anant Corporation and have been since about the beginning of the year. I started this series a few months back, with the first portion being on how to set up the environment that we work in with Cassandra and Spark. And then last month's portion of this series was on data preprocessing. Today we'll be talking about testing. Next time we'll be talking about validation and model selection tests. If you have questions during the course of this presentation, I ask that you put them in the chat, and I'll try to get to them either during the presentation, in between the presentation and the demo, or after the demo as we close up. We're talking today about how we test machine learning models. The talk is going to have an introduction. We're going to go over those three types of tests: binary classification tests, regression model tests, and multi-class classification tests. And then we are going to have a short demo about how you set up these things in the environment with Cassandra and Spark. So the first question, how do we test our machine learning models? Tests are generally just a statistical measure of how well our models work. We calculate them by running a model on data that was not used to train the model, also known as held out data, with known properties, and then comparing the predictions generated by our model to those known values. It works differently for different types of machine learning models, specifically based on what metrics they predict, and can be a problem if you are not working with predictive models at all. So these sort of tests that we'll talk about today generally don't work for clustering or for reinforcement learning tasks. And it's just generally an attempt to capture the potential performance of our model on data that the model will see out in a production environment. So next up, when do we test and on what data do we test? We can test whenever we have a trained model. And depending on what we find in our tests and where we are in the process, tests can have us proceeding onward to the next steps of deployment or returning back to previous ones to redo things like model selection and hyperparameter tuning. The same calculations that we use for calculating these test statistics can also be a part when run on the training data of the mathematical process for training our model in the first place. So this is the general process setup that we're using. We covered data pre-processing, which is over in the left part under preparation, and testing and validation sort of fall all up in these middle parts. So you can see in this that our data is split up into three different sets, and then based on what our model tells us about these data sets, we can tune the model, we can have it estimate outcomes on data that it hasn't been trained on. And depending on what that tells us, we finalize the model and put it out into production. The way we choose our data to train on, first, the rule is to never test on data that you trained on. Because machine learning algorithms often involve optimization on some of these metrics in your test, in your training data set. So testing on them only tells you information that you already know. And generally stops you from recognizing the things that you want to see in your actual tests, which tell you about how well your model works and whether it's overfitting or not. There are multiple methods for choosing data from your data set to help to hold out, but it should always be done randomly because the goal is that the distribution of the data you will see in production, the data in your training set, and the data in your test set are all the same. Generally, the simplest method, we split into training and testing data sets. but we can also split extra sets for final testing if we want to use our beginning tests to make choices about models or make choices about hyperparameter tuning. If you're using test data for that, you generally don't want to do your final testing on that same data. There are also more complex schemes called validation schemes, which will allow you to test on more data. And the test train split is the simplest one, and we'll be covering more of them in the next part of this series. So we're heading into our first set of tests for binary classification. Binary classifiers predict a value, which has a Boolean typing. It's either 0 or 1, true or false. It is sometimes framed as a focus on the presence or absence of a particular thing, and other times framed as choosing between two types or sorting things into two categories. In order to test our binary classification models, we build something called the confusion matrix. For binary classification tasks, confusion matrices are always 2 by 2 grids. We have class 1, in which in this case we refer to it as positive, and class 2, which we refer to as negative. And we build this 2 by 2 grid based on what we predicted, what our model has predicted for a particular example, and what the actual underlying label was. And we split that into these 4 categories. So true positives are values that you predict, class 1 or positive, and the truth, which you know because you collected this data with labels already, is also positive, which means you had a correct prediction and it's a positive value. A true negative is a correct prediction on a negative value. Your model guesses negative and the truth is also negative. A false negative is a prediction of negative when the truth of the matter is positive, and a false positive is a prediction of positive, but in actuality the value is negative. We then take these values and we combine them to compute more meaningful metrics. The number of true positives that your model generated by itself doesn't really tell you very much. The most commonly calculated metric from these values is accuracy. It's computed as the number of correct predictions, which is true positives plus true negatives, over all the predictions our model made. It's a general measure of how likely we are to correctly predict an example in the test set, and hopefully also generalizes to be the same as accuracy on data that our model sees in production. We also sometimes calculate recall, which is the number of correctly identified positive examples divided by the number of actual positive examples. And it tells us how well our model detects the presence of a positive value. So if we feed in a value we know is positive, it will give us a percentage value for how likely our model is to also tell us that that is positive. Precision is true positives divided by true positives plus false positives. And it tells us the reliability of the positive prediction. If we don't know what we fed in and what comes out is a positive prediction, we have this percentage chance of being correct about it. And then we sometimes combine recall and precision to calculate a composite value, which we call the F1 score or the F measure. The advantage of this is that if either recall or precision is low, the F1 score will also be low. And the good thing about that is that it emphasizes the importance of incorrect predictions, whereas accuracy emphasizes the importance of correct predictions. So depending on the cost of correct or incorrect predictions, we may want to emphasize one over the other in our analysis, which is sort of what we're going to focus on in this talk. The actual mathematical formulas can be looked up anywhere, but the meanings are a bit more tenuous. Essentially, if being wrong is particularly important to your model, and you want to know the the chances of that, you should look more at the F1 score. Whereas if you just need to know how often your model will be correct, you can look at accuracy. All right, moving on to regression models. Regression models do not have these same test statistics, but they do have something called test error. Regression models are machine learning models that estimate a function, which means once you have your model trained, you can feed in input values and it will produce a prediction in the form of a scalar value or multiple scalar values. Classification tests don't really work for regression models. Instead, the simplest component error metric, like a single value in one of the 4 blocks of the confusion matrix when you're working in regression, is just error, which is the difference between a predicted value and the actual value. Generally, when you get these values, you don't want to combine them by simple adding, because errors in different directions, at least errors along the same axis in different directions, will cancel each other out and cause problems in your later calculations and give you false ideas of how well your model is actually working. Instead, we use things like sum of squared error, where you take all your error values, you square them, and you add them together, or mean squared error, which is the same thing, except it's normalized by your number of examples. So you're taking the mean instead of just summing them. And then we also sometimes choose to calculate root mean squared error, where you take the value calculated for mean squared error and you take the square root, because the value of mean squared error comes back in whatever the units of your prediction are squared, whereas root mean squared error is translated back into the same units as your prediction. And you can see a graph here of basically how errors are calculated. So this is a linear regression. The function that it creates to estimate your data is a line. And the error, you go to the point on that line corresponding to the inputs, and you measure from the line to the actual example, and that is your error ratio. And then sometimes we prefer to use the absolute error rather than squared error in order to solve the problem of errors in different directions canceling out. And we calculate that by taking the absolute value of our error measures. We can then do the same summing or averaging as we would do with squared error. Sorry about that. And then the difference between using squared error and absolute error is that large error values, which can signify outliers in your model, are emphasized more by squared error measures. So in the same way that you might want to focus on errors in a classification task by using F1 score, you can focus on errors in a regression task by using squared error rather than absolute error. And we also use these same sort of error metric calculations on our training set when we're doing things like gradient descent. So for things like backpropagation of neural networks, the training of neural network models, we would generally decide to use squared error because of like mathematical features that the absolute value has, this discontinuity at 0, that make it difficult to do calculus on. So depending on what your further processing steps are for your calculated error metrics, you may want to choose one over the other. Moving on to confusion matrices for multiclass classification. Multiclass classifiers predict a value similar to binary classification in that it has discrete values, but there are more than 2. Regression models can predict potentially infinite values since they generate real numbers or other scalar values. But multiclass classifications are limited to a finite number of possibilities. We can't exactly build a 2x2 grid when we have 3 or more potential classes. So instead we build an n by n grid where n is the number of potential classes. Each test result gets placed in its cell based on what was predicted and what was the actual state. And we can't generally, in this state, label them as positive or negative predictions because we have 3 or more classes. And we also can't calculate accuracy or F1 score because we have 3 or more classes. So we don't have things that we can pull out like true positives or false negatives in order to do that calculation. So what we do here is we turn our n by n grid into n by n grids, where we treat correct predictions on whatever class that matrix is for as true positives, and then all other predictions are classified based on their relation to that class. So true negatives are not only correct predictions that are not for the class that the matrix is for, in this case class 1, as you can see in the example at the bottom, but they are also, even if they are wrong, if you are predicting not class 1 and the truth is not class 1, that is counted as a true negative here. And then our false positives and false negatives are also based on the prediction of class 1 or non-prediction of class 1. So a false negative is one where you predict not class 1, but the truth is class 1. And a false positive is where you predict class 1, but the truth is not class 1. So regardless of the actual values of those classes or the classes' relationship to each other, as long as they're not the class that the matrix is for. That's how we categorize our examples when we're building the individual confusion matrices. And we can take each of these confusion matrices, since they're now split into our 4 simple metrics, and we can calculate things like accuracy, recall, precision, F1 score. And we can then combine those values based on what's important for our application, like the choices we made up above in accuracy versus F1 score, or in squared error versus absolute error. We can do something called the macro average, where each class's matrix is scored the same. Or we can do something called micro average, where we weight each one by the number of examples that are represented in our training set. Macro average is a good general measure, but it can obscure very high or very low performance on certain classes that are not highly represented, or a class that is highly represented can fail to affect the average in the way that it maybe should. So if performance on particular classes is important to how your model works, important to the application that you're using, you may choose to micro average, or even just look at the scores for the individual matrices in isolation. One thing that I'd like to mention before we move into our demo, which we're about to do next, is that other fields, like specifically medical testing, have different names for these metrics and calculate different metrics out of the same true positive, false negative type values. So things like true negative rate, or things like positive predictive value that aren't super useful in most machine learning contexts, are also things that you can calculate from these values if it's important to your specific application. Okay. So we'll be moving on to a demo, which is not super related to all the mathematical stuff we talked about before, but will be a demonstration of where these metrics are in our environment with Spark and Cassandra. So we have set up these notebooks, and the details, all the details about how to bring up this environment, which can be found, the general idea, at Hades Architects CA Spark. It's something written by DataStax, which brings up containers for Spark, for Cassandra, and then for our notebooks. And then also the notebook that we are going to be using here can be found on my GitHub, though it may be moving to Anant GitHub soon. And if that's so, the correct link will be in the associated blog post and YouTube description. So we run this and it brings up our notebooks. Today we're going to be using some of the same data sets that we used previously for our data preprocessing episode for things like PCA. And those data sets are the IRIS data set, which is a popular one for learning machine learning, and then the Native American diabetes data set, which is up here on the GitHub. Both of them are. Okay. So compared to other parts of this series, things that are definitely unusual here as compared to what we've done in other series is that we are importing extra things. We're importing NumPy, and we are importing sklearn for their confusion matrix utilities, because all of the Spark-based things that I were able to find to do similar things are RDD based, whereas everything we've done in this series so far is data frame based. We have some helper functions up top, one for plotting confusion matrices, some for talking about correlation matrices, which are part of principal component analysis. So these notebooks currently are up here. But like I said, if they're moving to the Anant Discord, the correct links will be with wherever these recordings or the blog post associated ends up. So the first thing we are doing is we are loading our data into Cassandra, and then out of Cassandra into a Spark data frame, starting with the IRIS dataset, which has 150 examples, split 50 between each of the 3 classes. By the way, the helper functions for formatting of data frames like this and the other helper functions are all at the top of this notebook. Make sure to run those cells because I personally don't like the standard formatting when you try to print a data frame. So we can see the split between our classes, 50 for each of the 3 classes. This part is something we talked about in data preprocessing, where we take the 4 individual columns and combine them into one called features, which we will feed into our model. We perform our test train split, where 80% of the data is put into the training set and 20% of the data is put into the test set. And then the algorithm that we're using here is a random forest classifier, which takes a bunch of tree classifiers and combines their predictions. So we train them and we can see predictions here, which results in these predictions over here. And then the class that we're going to be using, which is in PySpark, is the Multiclass Classification Evaluator. The name makes it seem like it's only for multi-class classification problems, but it also works for your binary classification problems. This one is actually one of the multi-class classification problems because it has 3 potential classes for each example. But as we can see, we trained it. The accuracy is 96%. And we can compute both accuracy and F1 score using the multi-class classification evaluator. And then we can do some processing so that it matches up with scikit-learn's expectations. And then we can build our confusion matrix. So as you can see, we have correctly predicted 29 out of the 30 examples, 11 of which were from the first class, 9 of which were from the second class. Well, 10 of which are from the second class, and 9 of which are from the third class, although we got one in the second class incorrect. And then we can plot out our confusion matrix, where it will show a gradient for how many true positives, etc. you got. Well, this is building out the multi-class confusion matrix, but you can then take this and do the same processing where you take true negatives, true positives, and then these 4 would be true negatives. These would be false. Predicted label is not class A, and the truth is class A. So these would be false negatives, and these would be false positives. And then we can move on to our second data set. The Pima Indians diabetes data set is, well, it turns out to be a binary classification problem. And it does need some pre-processing because it has a lot of missing values, which we correct for. And the details of all of that are in the data pre-processing presentation, which is up on YouTube as well as the Anant blog already. Basically, what we are doing is we are figuring out which zeros are relevant, which zeros are not relevant, replacing all the non-relevant ones, and then removing them or filling them in with values that make sense, or removing those rows altogether. We do the same train test split and train our model. And we can see all the way over to the right, we have predictions. In this case, they are all either 0 or 1 because we're predicting a binary class. And then up here, you can also see they have a label already attached because this is our training data. Well, it's our test data, but it was gathered with labels already attached. So we do not have to guess. We know what these values should be. We do the same pre-processing to fit with scikit-learn's confusion matrix format. We calculate our confusion matrix. As you can see, this one is a bit less accurate, but we have 88 true positives, 29 true negatives. Which one is, this is the predicted negative, truth is positive, 21 false negatives, 9 false positives. And we can, the same way, use the multi-class classification evaluator in order to calculate accuracy for us. But we can also take the values from the confusion matrix and calculate the same things as well as F1 score. So you can see the value we calculated for our accuracy and the value that the multi-class classification evaluator calculated for our accuracy are the same. And we can also use those values to calculate the F1 score. All right, so we have some time for questions here at the end. If you have them, please put them in the Zoom chat, and I'll answer them as best I can before we finish up.
Hi, I've got a question. So in kind of a continuous learning process, I guess as you iterate through new training data, maybe new test data, and you get your accuracy and you get your recall and position, how could you put that, how could you save that information into Cassandra and then basically make decisions on how to tweak the model? I guess what I'm trying to say is, like, how would you have the output of the testing process saved so that there can be future automatic decisions made on the model later.
Okay. So the way, okay, so generally the thing you do at the end of this process, if you're working in this same Spark and Cassandra environment, is you save your predicted labels back as well into your original Cassandra table. But to keep track of accuracy, there are two general choices. You can save your model into a Cassandra table, or even just create a Cassandra table that has documents corresponding with each model that saves that data about your accuracy, your F1 score, so that when you retrain and recalculate these values, you can compare them. So each iteration will save its test statistics, and then when it's trained again, you will check back with those values, and if your model has gotten worse, you'll say, okay, that's probably not a good idea, go back to the last model. And if your model has gotten better, you can say keep it. Or if the performance hasn't changed and you're just getting more sure, you can also decide to keep it based on that. And your other option is to somehow label the data that you are putting back in with its predicted labels, so that we know which, basically like a tree ring of data, where each chorus, like as time increases, your data sets will be getting larger and larger. And then you can use those results to calculate on the subsection of your data that's currently in the Cassandra table, labeled that way, what the accuracy was at that point. So essentially,
Gotcha.
like, all this data is associated with version 1 of our algorithm. And
Gotcha.
that means that in that same iteration, we had this accuracy, this precision, etc.
Gotcha.
Why do you use pandas with Spark if pandas doesn't run in a distributed way? So we're using pandas not for its actual processing ability, in the same way that we're using scikit-learn for its ability to display the confusion matrices in an appropriate way. We use pandas in our data preprocessing section to display a correlation matrix, which we later use for principal component analysis. So it's not messing up the distributed processing. It's being used for some of the other properties. And Jay, we are not using PyArrow in this stack. It's built on DSE to get the Spark and Cassandra. There's a set of, there's a Jupyter Notebook set up, and then everything else is just being imported via Python. And we're just using normal PySpark. This specific pipeline, I would not say is suited for very high, like, since we are loading things into Cassandra in Python, and then loading things from Cassandra into the data frame where we work on them, I think this particular setup is not great for scalability, but Cassandra and Spark individually are, and all the processing is done in PySpark. So if you have a setup of Spark and Cassandra, say just a normal DSE cluster setup somewhere that you can interact with and run PySpark on, you can get scalability out of this same general sort of setup.
What is PyArrow?
Hey Jay, if you want to unmute yourself, you can go ahead and ask the question directly.
PyArrow, it's basically a way so that you don't have to use a JNI to basically recopy in memory the data set from JVM to whatever Python's doing with it, vice versa. Last I knew, the implementation for Spark was just for the driver. It's really only going to be useful, I think, for scalability with respect to the underlying distributed system if they get it to work on the workers as well. But there's workarounds with that, with depending on like what the optimization algorithm is, what the machine learning model is for certain data parallel methods, such as like with TensorFlow stochastic gradient descent, where you could possibly take advantage of Cassandra partitioning to do local slices for one batch locally, and have something like parameter tuner that's being tracked globally, like in say in a Spark cluster, ideally, or possibly something else, Cassandra, what have you. But yeah, really the interest. I was curious, like where folks were going, or where they saw things were going with respect to scaling out. And I think what maybe Rahul was getting to previously, with respect to using testing results, that's kind of key with respect to online model inferencing. One of the so-called holy grails of machine learning, so that you can uh, basically leverage the fact that during training, testing, validation, whichever, at one point for a particular statement, the math that's actually executing, for each type, for each phase, is actually the same. Your parameter state might be different, the intent might be different, where the data goes after that might be different, but for say a given neural network, the calculation that's being done for the inner product is going to be exactly the same with respect to the architecture and so forth. And that's also very interesting to me as well. So if you'd like to address that. Sorry if I was running over what it is you were asking or making too many assumptions there, but that's at least what I'm interested in.
Yeah, yeah. So is PyArrow related to the Apache Arrow project, which was related to? Okay. That makes sense. Yeah. Okay, that makes sense. Yeah, and in terms of like, could PyArrow be used? I believe if you have your featureized vector in PyArrow, PyArrow really is just making it easier to move that data around, because that's what I think the arrow format is, a binary format to store that columnar information, I believe. Another question for Obi. So generally the training process takes compute intensive resources, right? And once the model is created, technically the evaluation process could use the model on any worker node, right? So like, I think you mentioned, or I think Jay was mentioning, that you can store the model in Cassandra. So when a new piece of data comes in, or if a new piece of data needs to be evaluated, technically the Spark process could pull the model from Cassandra and evaluate it. Is that right?
Definitely sounds feasible. Generally, especially compared to testing and like normal operation of your model, the training is definitely the most resource intensive part. And even not working in distributed systems, one of the things you can do is have your model saved, pull it up, run it on new data that comes in, and put it away, essentially. So doing the same thing by having your model in the Cassandra table, having a Spark worker pull it, run the calculation, and put it back is definitely something that could be done.
So that would mean that you could have like a continuous training process continuing to update the partition that stores the model, while the Spark workers, I mean, they would basically get periodically new models because
Yes.
they're kind of fetching it from the same place. Okay.
Yes, depending on how your continuous updates work, it can be your worker is just fetching a new model every time a new piece of data comes in. If the model has been updated since last time, it pulls the new one, runs it, and then every time that happens, you get that new model.
Cool.
So just to follow up real quick on the PyArrow question, there's an implementation for main memory, but also GPU memory. So this is, I think, pretty interesting if you're talking about minimizing the fetching part to each worker, or say you might have a local model that is hot memory that might be better suited for the partition data that, say, for example, it might be COVID data for the state of Ohio or Virginia or some other region that might be more accurate with respect to that data that's sitting on that node, where it might make less sense perhaps to do copying over versus, say, using a model that's fairly hot in memory, or basically snapshotting, but not reproducing so much if you're talking about a very high performance tight SLA type requirement.
Yeah, I agree. I think there's room always for leveraging hardware optimized mechanisms for moving models and information. I think ultimately the benefit of leveraging Cassandra is the massive scale at which the persisted information can be spread.
Yep.
So technically what you're talking about could also be used in the same scenario, as in the actual evaluation engines of the Spark workers. If they have GPU, then they would essentially put it into via PyArrow into the GPU memory, and then as that is doing parallel processing and technically updating, let's say Cassandra with data, the information is moved around much more quicker than, there's probably different ways to move information. There's tons of different ways to move information. But having this kind of backbone between the training engine, the evaluation engine, the validation engine, and maybe the retraining engine based on the test data, all communicate via Cassandra as a layer, it just simplifies everything, because all you're doing is just, storing and retrieving information.
Right. So one of the things that I wanted to ask was about these different, let's say, training, testing, whatever phase that you have with respect to your deployment lifecycle. One of the key capabilities I think the system architecture would have to respect would be, guaranteed resource isolation in order to circumvent one of the primary concerns with respect to online modeling, and that is resource contention. As was mentioned, training is resource intensive. It's pretty well established, but one of the reasons why the models are typically deployed in a separate pipeline, a very circuitous route, I think, for scoring against models. But is there in the stack or data stacks or otherwise a way to provide guaranteed resource isolation in the case where that you have to have certain resources available for each of training and inference?
Well, I think the way you might want to handle things like that is just via containerization. We've talked about how your model training is the most intensive part. And really all that needs to actually make it from your model testing environment into from your model training environment into your model testing environment or into your deployment environment is the model itself. So one of the easy ways you could do that is to set up containers with like specified resources to do each of those three parts and transport the model in between them as they're ready for the next part.
Right. So for scalability for large systems, the networking, the overlay networks, routing, and so forth gets pretty complicated. Is this something that's being worked on, for data stacks, Kubernetes deployments, or otherwise?
I think in terms of resource allocation, definitely DataStax is not focused, or Cassandra or Spark is not necessarily focused on that. However, in Spark and actually in DSC, there is a way to assign different slots of worker pools, basically, and to have protection of certain resources for certain types of operations. Though what I think what Obi mentioned is also very accurate. What you're talking about is probably in the realm of not necessarily Kubernetes, but rather in an emerging space of basically platforms, data and analytics platforms, or even service meshes, where they run on top of Kubernetes. And maybe the end result that they're providing is an operator that takes care of a lot of this stuff. But so far as kind of optimizing the network, either Google is working on it, Docker is working on it, or maybe AWS is working on it to improve Kubernetes and then not give it to anybody. So yeah, definitely a good question to ask, but I don't specifically know of a large commercial company or an open source project that's necessarily doing that right now. Maybe some other people doing it.
All right, we'd like to finish up here today. If you would like to continue any of these conversations, I'd like to invite you to come to some of our other events, including Cassandra Lunch, which is held weekly on Wednesdays. We are Anant Corporation. We do things like architecture and engineering with Cassandra, Spark, and Kafka, working in specific programming languages, Node, Python, JVM. You can contact us at solutions.anant.us or via the phone number here. Thank you for coming. We would love to see you in the next part of this series or at any of our other events.
Thanks.
Thanks.
Okay. If nobody else has any questions, I think we'll go ahead and wrap up. Please, if you have any further questions or you want to discuss any of this material further, please reach out to us at solutions@anant.us. And again, I want to thank everybody for joining. I think this was a great discussion. And please check out our event page at anant.us/events and keep up with our upcoming events. Thanks, everybody. Have a good evening.